The first step is to turn the instrument on with the switch on the right hand side, just beneath the detector. It's right there. Then you want to double click on the wire 5.2 icon on the desktop. This will open the wire software. And then you want to make sure that the top radio button is checked that says reference unreferenced motors only, and then press OK. This will calibrate the motors in the system. Once this is complete, the software user interface should start up. If it doesn't start up, contact the support officer within MCFP. Next, we need to turn on the lasers for the instrument to allow them to warm up. We have 3 lasers on the instrument. We have a 633, a 532, and a 785 nanometer laser. You'll see that each of them has a key that allows you to turn the laser on, and the 785 also has a black button that you need to press to power up the laser. So to turn on either the 532 or the 633, you simply turn the key and you'll see that the laser light comes on. This module is now emitting the laser light. If you want to use the 785, you turn the module on with the key and you'll see the power light comes on, but the laser on light is not on. You then need to also press the black button and that will now power up the laser. You should give the instrument about 30 minutes for the lasers to warm up and for the detector on the instrument to cool down before you go ahead with your measurements. To open the enclosure door, press the black door release button, and this will allow you to roll open the door to gain access to the internal chamber. The stage you can then just gently pull out by grabbing onto this handle and pulling backwards, and this will allow you to mount your sample. The first sample that you should put in is the silicon sample, and this is just a silicon on glass slide sample. Place that on the stage, take the clip and firmly hold it in place with the clip. You can then slide the stage so that the silicon is then illuminated by the white light underneath the objective. The objective that should be in place is the one with the blue ring. This is a ×50 long working distance objective. Next, what we're going to do is bring the sample to close focus using the stage. And we do this by turning the large part of the black knob on the side of the microscope, and we rotate it away from ourselves so the top is going away, or it's clockwise if you were looking in this direction, to bring the stage up towards the objective. Pay close attention to the white spot from the white light illuminator, and you will see it collapsing down into a very bright spot on your sample. Get it to the point where it is its brightest. If you go too far, you will see the spot becomes large again and it is dull. So then back off again until the spot is the brightest. You should see now on the screen that the white light image has some light to it, whereas before it was very dark. So now you can fine tune the focus of the objective on your sample by using the stage. The stage controller has 3 axes and it has 4 speeds. Going from this position here, which is marked as red on the white card, this is the fastest, this is the next slowest, and this one is the slowest. If you're using the times 50 objective, generally you'd probably want to use these 2 speeds. So to start with, click the top left button. This will now activate the controller. The ball moves in X and Y, and the ring moves in Z. So if we now move the ring, we should hopefully see the sample come into focus. So here on the screen, we now see features on the sample. If we want to check that we're really looking at the sample, we can then move the trackball to make sure that different features are moving on the screen. If you go a long way out of focus, you will see that the image becomes dark again. If the image is becoming dark, go in the opposite direction to bring lightness back to your image until you find the focus. And then double check that you can move with X and Y. If you want to get a very fine focus, you can go to a slower speed by clicking a slower button here, and you'll see that the focus now changes much more slowly. The field stop control is this control here in the white light view control panel. It looks like an aperture with the letter F next to it. The slider goes from 100 down to 0, and as you close that down to 0, you see the aperture close across the image. The field stop aperture and the surface are both in the focal plane for the instrument. So when your aperture is in focus, the surface is in focus. If you're having trouble focusing on your sample, you can close down the field stop in the software, and this will put an aperture into the white light image. So when you bring your sample up towards focus with the black knob on the stage, if you look at the screen, what you'll end up seeing is rather than a full white image, what you'll end up getting is just a white circle in the center of the image that collapses down as you get closer to focus, and then you can see the aperture blades. When you can see this angular shape on the screen, this means that you're in focus with the surface, or very near to focus with the surface. When you get out of focus, the spot looks like a fuzzy circle and eventually goes black again. So this helps you quickly and easily get near to focus, and is particularly useful for rough samples. Again, you can get close with the knob on the stage, and then you can use the stage and the ring to do a fine focus. And then once you believe you're in focus, open up the field stop and find the position that you're interested in, and then do a fine focus to make sure you've got a sharp image. If you wish to change to a different objective on the microscope, first bring the stage all the way down so it is as far away from the objectives as possible. Now you can rotate this ring to change the objective. The times 50 is out by itself and is noted by this blue ring. We also have a times 5 objective, a times 20 objective, and times 100 objective. An important thing to note with all of these objectives is that the times 50 is a long working distance objective. So it is the safest to use in terms of how close you need to get to your sample to be in focus. To demonstrate this, we can now zoom in on the times 100 and I will bring this into focus. So we would have already passed the focal point of the times 50 objective by this point. And I can start to see now the white spot collapsing onto the sample to make a very bright spot. And I'm going very slowly at this stage. And the sample is now just coming into focus on the screen with a white image. And at this point, I now stop using the black knob on the stage because it is too coarse of an adjustment. So again, the final adjustment with the times 100 objective we do with the stage controller here. And here I'm also going to use the field stop aperture. So I pick a speed, one of the slightly slower speeds, and now I adjust this sample until it is in focus. And I slow right down to get the sharpest focus. And what you will see, of course, is that with the times 100 objective, if we use this speed that we were using before with the times 50, it is now very fast. So we need to use a slower stage speed to give us better control. You can see just how close the times 100 objective gets to a sample before it is in focus. It is within around 300 microns. Because of how close the times 100 objective is to your sample, do not make coarse movements of the stage while you're in focus, and do not change the objectives while you are in focus. Before you do either of these, bring the sample down all the way to the bottom, and then you can either exchange your sample or change the objective. Now close the door to the enclosure because we're going to be powering on the laser. Rotate it until it clicks. Once the sample is in focus, we now want to bring the laser down onto the sample to ensure that the spot position is in the center crosshairs. So first of all, ensure that you have the laser module powered on. Double check here that this objective is set to the correct value. You will see that this says times 5, whereas we're using the times 50 objective. So pull down this menu and change it to the times 50. You may need to refocus again. Now we want to view the sample and the laser. So click this button here, which is the camera and the laser target reticle. This will allow the laser light to come down onto the sample, but it doesn't yet because the shutter is still closed. So this button here will open the shutter for the laser. And you can see we have a very bright laser light on the sample. So now turn the laser power down. And we want to get it to the point where we can only just see the laser spot on the sample. So to do this, we need to turn off the white light. So you click the light bulb button here to turn off the white light. And you will see that the green laser spot, this is the 532 nanometer laser, is not in the center. If we increase the power, you will see the laser spot gets brighter and brighter. When it's large like this, it's very difficult to tell whether it's exactly in the center because there's so much scattered light. So this is why we want a very low laser power. You can also check your focus here by again going to the stage and moving the outer ring, and you can see when it is in focus, when the spot is the smallest. To shift this spot into the center, we need to go to Tools, Manual Beam Steer, and then we are going to change Beam Steer Left only. Do not change Beam Steer Right. So now steer this spot into the center of the image with the crosshairs. So if you feel like the spot needs to go right, click right. And then you can click it a few times to start to move the spot towards the center. Now we feel like we need to go up, so click up. What you will see is that up doesn't really mean up, it's more of a diagonal motion. So this brings it closely into the center on this axis, but now we need to come left again. So click the left arrow to bring the spot more into the center. And again, you can now move up and down with your focus and just see if the spot is nicely in the center, and it looks like it is. Once you get it centered, click OK, and then save the current motor positions. Next, we need to check the calibration of the instrument. So the first thing we're going to do is open up a measurement template to check this calibration. So to do that, we go to Measurement, Open Measurement Template. And now you need to find the correct template to use for the laser and the grating that you are currently using. We are using the 1800 line per millimeter grating, and we are using the 532 nanometer laser. So I need to find the 532 nanometer 1800 template, and then there are two of those. There's one for confocal and one for regular. If you are just doing normal spectroscopy, you would choose the regular daily check. Click this and then click OK. This opens up a measurement template that we can then run. So to run this template, click the Run button, which it looks like a big play button. The instrument will now set the laser and the gratings to the correct position and make a predefined measurement. So what we can see here is the Raman spectrum from the silicon sample. So we want to check the height, the position, and the width of this peak. So to do that, right-click on the spectrum, go to Tools, and Curve Fit. And now if you want to zoom in on this peak to make it a little bit easier for yourself, you can left-click, draw a box around the peak, let go, and then left-click inside that box to zoom in. Now, if you just left-click once, you'll create a component. Now right-click and go to Start Fit, and the software will fit that component to your spectrum. What we want to check is the center, width, and height of this peak. We want the center to be 520.5 plus or minus 0.5. So you can see that this is not quite correct. We want the width to be less than 5, and the height, we would like to see more than 25,000 here, ideally. So you can see that these two values are good, but this center position is not correct. So this indicates we need to calibrate the instrument. So close the curve fit by clicking the small cross. Now go to Tools, Calibration, Quick Calibration, and let the instrument run this calibration. You can see it gives a dialog box to tell you that it's done the job. Click OK and close that window. Now we click this template again and we rerun that template. And perform the same operation. Right click, Tools, Curve Fit, left click on the peak, right click, Start Fit. And now what you can see is the peak reads 520.5 and it is within the plus or minus 0.5. The width is still less than 5 and the height is still more than 25,000. So this now indicates that the instrument is operating the way that we want it to operate. You can close the curve fit, and now we want to save this data. We go to File, Save File As, and we want to go and find in the Renishaw data directory here, a folder called Daily Checks. Open this, and now we are going to save this file so that we have that data for later on. So we are going to call this 2020-07, and the date today is the 10th. And I'm going to put my initials and then indicate that this is a regular check. We are using the 532 nanometer laser and the 1800 grating. And then click Save. You can now close that measurement template and the instrument is now ready to be used. When you're ready to make a measurement, you need to insert your sample and focus on the sample in the same way that we did at the very start. If you don't see an image on the screen, you just see black, it could mean that either the sample is out of focus, or it could simply mean that the camera has not been turned on and the illumination has not been turned on. So to turn on the white light image, you can click the camera button and now you can see that we can see the sample again. Similarly, if the image is black like this, but the white light image button is activated, then simply turn the light on. You can control the illumination of the light with this slider, and you can also control the brightness of this image by hovering over this gear here and changing the exposure time. Moving the exposure time slider to the right makes the image brighter, and moving it to the left will make it darker. Find the region that you want to look at using the stage controller and make sure that you're in focus. To start a new spectrum measurement, go to Measurement, New, and Spectral Acquisition. This will bring up a new dialog box for you to set up your conditions. The first thing you want to think about is the range. So this is how wide your spectrum is going to be. When you're using a static grating scan type, you have a fixed range and you can only change the center value. You'll notice that when the center is 520, for example, on the silicon peak, the low range is negative. So we can't capture information down here. So we might want to change this value to say 1000, for example. Now you can see our spectrum range goes from 60 to 1800. If you want to do an extended scan, you can click this radio button, and now you can change the low and high values. Note that this takes a lot longer and the data tends to be noisier. So whenever possible, the static scan is the best option. The next tab is the acquisition tab. Here you can change your exposure time, your laser power, and the number of acquisitions. Generally, you can leave the exposure time as it is, and you don't always need 100% laser power. And in fact, with many samples, this will probably damage your sample. So you might want to choose a lower laser power. Here I'm going to choose 5%, and I'm going to do 5 accumulations. So this is 5 scans. Next, we want to change the file name setting to make sure that we save these data. So click on Browse and find your folder within the Renishaw data directory. And if you don't have one, feel free to create one. I'm going to create a new folder here for today, and I'm going to call this data set test. I'm then also going to check auto increment and auto export to text. Most of the other tabs along here don't really matter for a normal spectrum. So now you can just click apply, OK, and it will bring up this measurement window for you. And then you can simply run your measurement. Now we see it collects 5 scans of the silicon sample. This file will be automatically saved. If we go to the Renishaw data directory and the folder I created, you will see that we have the wire data file automatically created, and we have the text file automatically exported. I clicked auto increment as well. So if I want to repeat that measurement immediately, I can click run. It will automatically recreate or recollect that data set, but it will not overwrite the previous file. Instead, what it will do is it will increment the number afterwards. So this is a very safe way for you to repeat data sets without worrying about overwriting files. Another measurement type that you may be interested in using is mapping. To start a mapping measurement, go to the measurement window, New, Map Image Acquisition. This is a simple way to create an area of Raman spectra. So you now, within this dialog box, go to this pull-down menu and select Rectangle Field. And you can now draw a rectangle around the area that you wish to map with the Raman instrument. The next thing you need to set is the step size between each of your points. So here, a 1 micron step size means we are going to collect 3,626 spectra within this rectangle. This is too much for a demonstration, so I'm going to increase this step size in both X and Y to 10 microns. And now we have an 8x6 grid giving 48 points. You can now click OK, and it will bring up the measurement setup. The conditions here are the same as what you did for a spectral setup, except now I would definitely favor using only the static grading scan type, because this will greatly increase the speed that you can acquire the data. So here I'm going to set the center again to 1000, acquisition 1 second, I'm going to keep 5% laser power, and this time I'm only going to do a single accumulation of each point to make it quick. Again, set a file name. So I will call this Test map. I'm going to auto increment and auto export to text. Click OK, and now your mapping measurement is set up. Just click run like you did before, and now what will happen is the measurement window will change to a mapping review window, and you can maximize this window if you like, and it is going to show you the white light image and the spectrum from each point. So you can see it very quickly goes across and captures a spectrum at each point that you've set within that grid. Once complete, we'll be able to quickly cycle through all of these different positions, and we'll also be able to map the intensity of a peak across this area. Once the data collection is complete for the map, you might just end up with only the spectrum here. You can switch through the different spectra throughout your map using these cycle buttons up in the toolbar, but this is not particularly visual to tell you what's going on across that area. So if you would like to view the map data again, you click on the spectrum, go to view and view map data. This now gives you the white light image and the spectrum. You can maximize this window. And now what you can do is you could click into different areas in your map, and it will show you the spectrum from that map, that area in the map. But again, we would like to actually map intensity of peaks here. So to do this, go to Analysis and Mapping Review. And this will now allow you to create maps. So we can create a map from an intensity at a point, a signal to baseline, signal to axis, peak area, peak position, peak width, peak intensity, and some other more complicated ones. We're going to do signal to baseline. So click signal to baseline and then click create. It will now bring up a representative spectrum from the sample that you can use to fit the peaks, or to choose the peak that you're going to measure. So here we're going to pick this sharp peak related to silicon, and I want the first and second limits, as in the points for the background or the baseline, to sit around that peak. If you need to see closer, you can left click and draw a box around the peak, let go, and then click inside the box to zoom in. And you can more precisely adjust these limits. If you want to zoom out again, you can click the zoom out button here to see. And now what we're going to do is click this little map icon to create a new map. So that has created a map here with a baseline from 481 to 568. Just to show you what it looks like to create another one, I'm going to also capture this flat top peak as well. And now what you want to do is select both of these maps and click View. So now from the Raman spectra across your mapped areas, it has mapped out the intensity of these two peaks and created two different intensity maps for you to view. And you can change the visibility of these relative to the white light image. So this could be useful, for example, if you're looking at the ratio of two peaks, or you wanted to look at the intensity of different components from your sample. You may wish to actually map a ratio of two peaks. So to do this, again, go to Mapping Review, create the maps for the two peaks that you're interested in, and then go back to the menu and select ratio here and create. And this now allows you to take a ratio of two different maps. So here we're going to take the large peak divided by the small peak. Create map, select that and view that. So now this map is a ratio of this map divided by this map. So this could be useful for a D to G ratio with graphene and carbon samples, for example. The instrument has 3 different gratings to use between the 3 different lasers. At all times at the moment, the gratings that are installed are the 1800 line per millimeter grating and the 1200 line per millimeter grating. The reason for this, we can see if we look at the measurement templates. You will see that only certain gratings can be used with certain lasers. An easier way to see this information is if we look at these template files. You will see that for the 532 nanometer laser, we can use the 1200, the 1800, and the 2400 grating. What this gives us is increasing spectral resolution and decreasing spectral width when we collect data with the 532 nanometer laser. However, what you will see is that the 633 nanometer laser is currently only set up to operate with the 1800 grating, and the 785 nanometer laser is only set up and can only work with the 1200 grating. That means that at all times we have in the system the 1800 and the 1200 grating accessible to the user. The 2400 grating requires us to swap out one of the gratings and would be a special request to us. Along with the different gratings, there are 2 different filters that are present in the system as well. For the 532 nanometer laser, the cutoff filter is a 100 wave number filter. So if we look at this spectrum of silicon and we zoom in at this low wave number region, you can see that the signal here drops off at around 100 wave numbers. So there is very little signal below 100 wave numbers, so there's not much value in collecting data below this point. For the 633 and the 785 nanometer laser, the cutoff filter is 50 wave numbers. So you can go a little bit lower with your spectrum, but below 50 wave numbers, there is very little to gain by collecting data there. When you've completed your measurements, open the enclosure, drop down the stage, pull the stage out, unclip your sample and remove it. If it is your sample, take it with you. In this case, this one stays with the instrument. Close the enclosure again. Shut down the software. Power off the laser module that you are using by turning the switch. And then power off the instrument at the switch.